Did you know that hot water freezes faster than cold water? I know it sounds absolutely ridiculous, right? Hot things should take longer to cool down. Well, under the right conditions, hot water actually can freeze faster than cold water. However, this has remained controversial for decades. This phenomena is called the Mpemba effect, named after a Tanzanian student, Erasto Mpemba. In 1963, when he was just 13 years old, Mpemba was making ice cream in his school's cooking class. He noticed something strange. When he put his hot ice cream mixture in the freezer, it froze before his classmates' cooler mixtures did. When he mentioned this to his teacher, he got ridiculed. His teacher literally told him he was confused and this is impossible. But Mpemba persisted. Years later, when a physics professor named Dennis Osborne visited his school, Mpemba asked him, "If you take two similar containers with equal volumes of water, one at 35 degrees Celsius and the other at 100 degrees Celsius, and put them in a freezer, the one that started at 100 degrees will freeze first. Why?" Professor Osborne actually decided to test this instead of just dismissing it. And guess what? The hot water really did freeze faster. In 1969, they published their findings together, and the Mpemba effect was born. But here's the thing, Mpemba wasn't even the first to notice this. Aristotle mentioned it in the 4th century BCE. Francis Bacon wrote about it in the 1620s. René Descartes discussed it in the 1630s. But all of them were dismissed or forgotten because it seemed so obviously wrong. Let's talk about why this seems so counterintuitive. Basic thermodynamics tells us that objects cool down at a rate proportional to the temperature difference between them and their surroundings. So, if you have water at 90 degrees and water at 30 degrees in a freezer at minus 20 degrees, the hotter water has further to go. It needs to cool down 110 degrees to freeze, while the cooler water only needs to cool down 50 degrees. Common sense says the cold water should win every time, but nature doesn't always follow common sense. So what's actually going on here? The exact mechanism is unknown, but there are likely several factors at play creating this effect together. First, there's evaporation. Hot water evaporates faster than cold water. Obviously, when water evaporates, you are losing mass. Less mass means less water that needs to freeze. Plus, evaporation is an endothermic process, meaning it removes heat from the system. So the hot water is actually losing heat through two mechanisms, regular heat transfer and evaporative cooling. Hot water also creates stronger convection currents than cold water. These currents circulate the water more vigorously, which can lead to more uniform and efficient cooling. The movement brings warmer water to the surface, where it can radiate heat more effectively. Third, supercooling. This one's really interesting. Cold water is more likely to supercool, meaning it can drop below 0 degrees Celsius without actually freezing. Hot water is less likely to do this because it has more dissolved gases driven out during heating and fewer nucleation sites for ice crystals to form. Hot water may also have a different hydrogen bond structure compared to cold water. When water is heated, these bonds stretch and store energy. When cooling begins, this stored energy can actually help the cooling process in ways we are still working to fully understand. Finally, there are environmental factors. Well, several ones. The container matters. How it sits in the freezer matters. Frost buildup on the bottom of a cold water container can actually insulate it and slow freezing, while a hot water container might melt this frost initially, creating better thermal contact with the freezer's surface. Once you understand these mechanisms, the Mpemba effect starts to make sense. It's not that the heat directly helps the water freeze faster, but rather the heat sets up a series of conditions which, if they work in tandem, can lead to faster cooling. Think of it like two runners in a race. One runner starts closer to the finish line but runs at a moderate pace. The other runner starts much further back but runs faster, takes a more efficient path, and even loses some weight along the way by shedding equipment. Under specific track conditions, that second runner might actually cross the finish line first. The key phrase is under the right conditions. The Mpemba effect doesn't always happen. It depends on the initial temperatures, the container, the freezer conditions, and probably factors we haven't even identified yet. This is why it has remained so controversial. It is not exactly reproducible in every experiment. Today, scientists continue studying this effect using advanced techniques. Some researchers have examined it at the molecular level, looking at how individual water molecules behave. Others have created computer simulations to model the various factors involved. In 2016, a new theory proposed that the key may lie in how energy is distributed among the water molecules, with hot water actually able to relax into a frozen state through certain energetic pathways that cold water cannot access as easily. So what does the Mpemba effect teach us? Counterintuitive doesn't mean impossible. Sometimes nature operates in ways that defy our initial expectations, and that's what makes these discoveries so unpredictable and mesmerizing. It also reminds us to listen to careful observers, even if they are 13-year-old students making ice cream. Erasto Mpemba trusted what he saw, asked questions, ultimately got the phenomenon named after him. Science is full of surprises, you just have to be willing to look for them. Thank you.